Okay, in this video we're going to talk about Saturn's largest moon, Titan, and some interesting and maybe a little unexpected things that we've learned about Titan only in the past, let's say 15 years or so. When you look at Titan from the Earth, you don't see much because Titan is covered completely in clouds. So we've known about Titan for a really, really long time. In fact, Titan was discovered just a little bit after Galileo discovered the moons of Jupiter. It was discovered in the mid-1600s. Hold on just a second. By a Dutch scientist named Christian Huygens. Most Americans are lazy and just pronounce his last name Huygens, which I will do when I talk about the space probe. But Christian Huygens was sort of a contemporary of Sir Isaac Newton. Remember, Newton published the Principia in 1687. Titan was discovered in 1655, so Isaac Newton knew about Titan. He knew there was a moon orbiting Saturn, and he used the moons of Jupiter and Saturn both to help construct his theory of gravitation. Christian Huygens wrote about the Saturnian system, again in 1655, in which he noted that Saturn is surrounded by a ring that goes all the way around the planet. Remember when Galileo looked at Saturn, he kind of drew it with two bumps on the side, almost like little ears. He didn't really understand that the ring was disconnected. So 50 years after Galileo, we had better telescopes that could make out a better image of Saturn. And he also discovered this tiny orbiting moon that goes around Saturn. And I think Huygens actually named it Titan. So we've known about Titan for a long time. Saturn has lots and lots of moons that we've discovered since I think I mentioned in the presentation about Saturn that I stopped counting how many moons Saturn has. It's more than 60 altogether, depending on if you count the ones that actually orbit in the ring system. 50 named moons, a dozen or so unnamed moons. 7 moons that are big and large enough to be spherical. Remember, I think we said a few times in the class that once an object is massive enough, gravity will squeeze that object into a sphere. So the reason all the planets and large moons in the solar system are spherical is because gravity squeezes them into a sphere. A small moon like Mars's moons can have this kind of irregular potato shape because there's not enough gravitational force to squish them into a sphere. So Saturn has 7 big moons, and today we will talk about Titan in particular. Titan is larger than our moon. It's second in size only to Ganymede. Ganymede's a little bit bigger than Titan, so I said, did I say it was the largest? It's one of the largest moons in the solar system, second only to Ganymede. But it is the only moon in the solar system that has an appreciable atmosphere. When we look at Titan, we do not see its surface, we see its cloud tops, which raises the question of what is going on under there. And that's what the Huygens mission was designed to discover. Titan all by itself makes up 90% of the mass of the stuff orbiting Saturn. So if you take all the junk in the rings and all these other moons and scoop them all together in a ball, it would still be less than 1/9 the mass of Saturn. So most of the mass orbiting Saturn is contained in Titan, and these other moons, Mimas, Enceladus, Tethys, Dione, are much, much smaller. So we're not going to talk about them, except for maybe we're going to talk a little bit about Enceladus near the end. The atmosphere of Titan we've known about, again, for a really, really long time. It is largely nitrogen, just like our atmosphere is largely nitrogen, about 98% nitrogen, with a small amount, a little less than 2%, of methane, and then trace amounts of other gases. We have known about this via spectroscopy for a really, really long time. The question is, what's going on underneath that atmosphere? And what is the reason, or what is the source of this methane? Methane is fairly chemically reactive, and so if there's methane present in an atmosphere in large amounts, there's probably some kind of chemical process that's replenishing that methane, just like oxygen in our atmosphere is indicative of the fact that biological processes are replenishing that oxygen. Saturn's far from the sun, 9.5 astronomical units, not quite 10, so it receives almost 1/100th the amount of sunlight, the amount of light and heat that the Earth does. Remember, light follows an inverse square law, so if you're 10 times further away, that's 1/100th the amount of sunlight. So Saturn receives a little more than 1% as much sunlight as the Earth does, which means the temperature is cold. The temperatures at the cloud tops of Saturn, remember, were about 300 degrees below 0 Fahrenheit. So we expect that the surface temperature of Titan is likewise about 300 degrees below 0 Fahrenheit. Its atmospheric pressure is actually larger than the Earth's atmospheric pressure. The atmospheric pressure on the surface of Titan is 1.4 atmospheres. So the atmospheric pressure is comparable, actually larger than the atmospheric pressure here on the Earth. There is a layer of haze that obscures our view of the surface. There are clouds in the atmosphere of Titan, we know now, and this haze layer actually reflects some sunlight. So the top of Titan's atmosphere is actually a little bit warmer than the lower levels. They actually call this an inverse greenhouse effect. The clouds in the upper atmosphere and the haze layer in the upper atmosphere reflect some of the light falling on Titan. So you can think of it as this light goes through the upper atmosphere twice and heats it up more than the lower atmosphere. So the upper atmosphere is a little bit warmer, about 170 degrees below 0 Fahrenheit. That's still cold by Earth standards, but it's about 100 degrees warmer than the lower atmosphere and the surface of Titan, which is unusual. Usually we think of atmospheres as being colder at the top and warmer as you go deeper and deeper and deeper. There are also trace amounts of organic compounds. All organic means is it's based on a chain of carbon atoms, right? So it doesn't necessarily mean associated with life, although life on Earth is made of organic molecules. There are organic molecules in the atmosphere of Titan like acetylene, ethane, propane. Some of these are flammable. These are just hydrocarbons. We use these in a gas grill. We use acetylene in torches. Hydrogen cyanide, which is a deadly poisonous gas, but it is an organic molecule, and it is actually can be used as a building block for more complicated organic molecules. There are also trace amounts of helium and argon, noble gases, a little tiny bit of carbon dioxide, carbon monoxide. So Titan's atmosphere is fairly complex, and the fact that we find organic molecules like this in Titan's atmosphere is interesting because it may be a useful model for what the atmosphere of Earth may have been like very, very early in Earth's history, even though it's very different from the Earth's atmosphere. Now, this mixture of organic molecules we find in a lot of places in the outer solar system. When we look at Jupiter's moon Europa, we see this big orangey brown stain on the surface and the orange and brown coloration of these long stripes that crisscross the surface. When we look at Neptune's moon Triton, we see these areas of this sort of orange-brown coloration. And these mineral and chemical compounds we find in the outer solar system have been given the collective name Phtholons by astronomer Carl Sagan. Phtholons just describes a kind of orangey brown goop of organic molecules found on the surfaces and atmospheres of moons and objects in the outer solar system. So the source and origin of this organic chemistry is of interest to us because we are interested in the process by which simple organic chemistry becomes complex organic chemistry, which becomes biochemistry, because that is the process that led to life on the Earth. And the more common we find these simple organic molecules, the building blocks of more complicated organic molecules, like say amino acids, which our bodies build into proteins. The more common these chemical compounds are, the more confidence we have that the organic chemistry that was a precursor to biochemistry is a fairly common set of processes in the universe. Here's Neptune's largest moon, Triton, and again you can see this kind of orangey coloration that probably comes from ultraviolet light from the sun driving chemical reactions between carbon compounds like CO2 and methane fusing them together into bigger and bigger and bigger organic molecules. I'm no chemist, but all you need is CO2 or methane and some energy to start building those short organic molecules into longer organic molecules. In the atmosphere of Titan in particular, you have things like methane and ammonia, which some ultraviolet light from the sun can cause to combine into things like ethane and release some hydrogen gas, and that hydrogen gas will just escape from the atmosphere. Or hydrogen cyanide, which you find in the atmosphere. And that can eventually build into longer and longer change into things like propane, or stick a couple hydrogen cyanides together and you can get cyanoacetylene, and so on and so forth. None of which are particularly important biomolecules on Earth now, but may have been important building blocks early in the Earth's history for the types of organic molecules that do become the important building blocks for life on Earth. There is a famous experiment in the history of early biochemistry, thinking about the origin of life on Earth, called the Miller-Urey experiment. In the Miller-Urey experiment, they just mixed together the kinds of gases they thought would be present in the Earth's early atmosphere: hydrogen, carbon dioxide, methane, ethane, maybe some ammonia, CO2, and just ran electricity through it and ran ultraviolet light through it. And what happened is the interior of that container became coated with this orangey brown goop of organic molecules that had these simple organic building blocks in it. Well, that orangey brown goop on the Miller-Urey experiment does not look terribly different from the orangey brown goop we find in Titan's atmosphere or in the surfaces of Europa or Triton or Pluto's moon Charon. So one way that we can think of Titan, Saturn's largest moon, is as a planetary-sized Miller-Urey experiment. And what was the goal of the Miller-Urey experiment? It was to explore what kinds of chemical reactions might have been going on in the atmospheres and oceans of the early Earth, when the Earth had just solidified and the oceans had just condensed out of vapor and the atmosphere had just become stable. At some point, life formed, but before that, the organic building blocks of life had to form. And studying that prebiotic organic chemistry is one reason that astronomers and astrobiologists are very interested in Titan. Not necessarily because we think Titan might have life, although it might, but because we think that Titan is a place to observe processes happening in the atmosphere that would have been happening in the Earth 3.5 billion years ago. One interesting possibility that we've known about for a or we've considered for a very, very long time is with a temperature on the surface of around 300 below 0 Fahrenheit, and with atmospheric pressure to help keep a liquid from evaporating, that it might be possible that there would be liquids on the surface of Titan. For example, methane, CH4, has a boiling point between 297 Fahrenheit and 259 Fahrenheit, below 0. That's right in this range. Ethane, which is a slightly larger organic molecule, C2H6, has a boiling point between 300 degrees 0 below 0 Fahrenheit and 127 below 0 Fahrenheit. Again, the surface temperature of Titan falls right within that range. So when we decided to explore Titan directly, one of the things we were looking for is evidence for standing permanent bodies of liquid, not liquid water, but liquids like methane and ethane on the surface. So that when we sent the Cassini probe to Saturn, we made part of that probe a lander to land on Titan. So Cassini is the probe that orbits Saturn. Huygens is the lander that landed on Titan. Our first view of the surface came from the, I believe these are ultraviolet camera images taken by the Huygens probe on its way to Titan. And we can already see, before it even enters the atmosphere, the outlines of something on the surface that looks like, at least if we saw something like this on the Earth, we would say that looks like a coastline. As the probe descended, this image became clearer and clearer and clearer, and we get views of the surface of Titan. This is actually, I think, a combination of a photograph and a radar map, where the dark regions appear to be perfectly flat surfaces, much like the surface of a body of liquid. Again, not liquid water, but possibly a standing body of liquid ethane and methane. We see coastlines that look like they're formed by erosion, and we see things that look like the mouths of rivers, which would mean that not only are there standing bodies of water, but there's flowing water on the surface. We see things that look, this could be, if I didn't show you what this was, this could be a photograph of the place that the James River opens out into the Chesapeake Bay. It looks like what we associate with a coastline on the Earth, mouths of rivers, little disconnected islands in this liquid sea, let's call it, in the top part of the photograph. Again, very, very similar to what we would think of as the appearance of a coastline. That, I'll be darned if that doesn't look like a river flowing downhill to the sea. So Saturn's moon Titan is the first place where we have discovered standing bodies of liquid. I almost said water, but it's not water. Standing bodies of permanent liquid on the surface of another astronomical object. We've even seen places where the level of the liquid seems to change over time. This is a picture taken as the probe went down into the atmosphere at a kind of an oblique angle, showing these smaller, what look like sort of ponds or large puddles on the surface as the probe went down. Again, here's a map of the surface with some grid lines overlaid on it to show you the North Pole of Titan is right there. Some of the places were not photographed, but in between the places, you see these large seas with what looks like a coastline with liquid flowing into them. If there is flowing liquid, by the way, these are big. This object, this standing body of liquid is about the size of Lake Michigan. So these are huge bodies of liquid on the surface of Titan. If there is flowing liquid, I mean, this looks like a river, right? A river flowing down from the hilly parts down into this lake here. If there is flowing liquid, that means there has to be precipitation. Right? Rivers can't flow without something filling up the river at the top of the hill, right? Rivers would empty out if there wasn't rain that filled up the rivers and kept those rivers filled with liquid. On the planet Earth, we call that the water cycle, right? Water evaporates from seas and lakes, it makes clouds, those clouds rain on the hills, that water flows down in the river, winds up back in the sea or the lake again. Which means Titan also has to have precipitation. It would be the only other place in the solar system we know of that has quote-unquote rain, or at least drizzle. We don't think it rains on Titan the way it does on Earth. There's no downpours of liquid methane and ethane. There's probably sort of light drizzles of methane and ethane all the time. So again, the evidence from the Huygens probe is very, very clear that there is flowing liquid on the surface of Titan. We image the clouds, and we can actually see, when we do spectroscopy of these clouds, we can see clouds made of ethane. So we know that there is a cycle of evaporation and precipitation on the moon as well. Again, I said this a minute ago, just to reiterate, probably not downpours. There's probably what we would think of as methane drizzle. Think of the kind of rain they have all the time in London, just a kind of a light misty rain, and maybe ethane snow, where the ethane freezes out from the clouds into ice crystals that then fall from the sky, a sort of flurry of ethane that then lands on the ground and then melts, and that ethane flows back down to the lakes. So we do believe that Titan has weather, precipitation. We haven't kind of measured this directly, so measuring how much and how often and how furiously it rains and snows on Titan is a job for a future space probe. We do see the seasons on Titan changing. Now, Titan goes around Saturn, right? And Saturn goes around the sun. So Saturn takes, what, 35 years, I think, to go around the sun once, something like that, which means the seasons on Titan will be very, very long. They will be, what's that, 8 years or so long, Earth years. But we actually see seasonal changes on Titan as it goes from being summer in one hemisphere to summer in the other atmosphere, an increase in the evaporation of the liquid in the bodies of water in the other hemisphere, leading to more clouds in the atmosphere. We can actually see places where it's dry during part of our observation of Titan, and then when we observe that same section of Titan later, that region is now filled up with liquid. So the lakes and seas on Titan change their how full they are of methane and ethane as the seasons change. This is what the surface of Titan looks like. Notice it's not very bright because you're 10 times further away from the sun, and there's this thick atmosphere blocking out the sun. This kind of orangey haze is what you would see when you look into through the air of Titan. This is from the Huygens probe, which landed in 2005. So again, about a little more than 15 years ago. The Huygens probe didn't send back a lot of pictures, but the pictures look sort of like this. And what you see when you see these rocks, you may say, well, those are just rocks. What does that tell me? First of all, the rocks are smooth. And what causes rocks to be smooth is erosion. Right? Rocks would not be smooth unless there was a process of wind and rain and weathering that would smooth those rocks out. So the smoothness of the rocks is indicative of the fact that this rock has been subjected to millions, if not billions, of years of ethane and methane rain and wind in the atmosphere of Titan. So here's an object in our solar system with oceans, not water oceans, but some kind of oceans, with an atmosphere, and with some kind of active organic chemical processes, which raises the question, anytime we find those sorts of things, could it be possible that Titan has life on it? Can we imagine life existing in an ocean of methane and ethane as opposed to an ocean of water? When we talk about astrobiology, I'll give a separate lecture just about water and what it is about water that makes it so good to be alive in, or have in you, right? Our bodies are largely made of water. What is it about water chemically that makes it a good candidate for a liquid to be the basis of chemical processes that lead to life? There is some evidence nowadays that just like under the surface of Europa, just like under the surface of Ganymede, there may be liquid water underneath the surface of Titan. This evidence is, I think, still a little more circumstantial and indirect than the evidence for Ganymede and Titan, but we're starting to get this picture where a lot of the large moons in our outer solar system are thought to maybe have liquid water under the surface. If there's organic chemistry and oceans and an atmosphere and liquid water under the surface, maybe Titan is another place in our solar system that we shouldn't rule out as a possible location where there could be at least simple microbial life. So that's a good reason to keep exploring Titan in the future. Could there be life in the methane and ethane seas? It's hard to say. Again, we haven't talked yet about the properties of water that make it good for living in. But one of those properties, just to talk about it very, very briefly, is that water is a very polar molecule, meaning you've got the oxygen, it's H2O, right? You've got oxygen and two hydrogens. The H2O are not in a straight line. It doesn't go H, O, H. It goes H, and then the O, and then H, and this is like 120 some degree angle. And the two hydrogens are positively charged because the oxygen borrows their electrons. So the oxygen has a negative charge. The two hydrogens have a positive charge, which means a water molecule kind of has a positive end and a negative end, which means it exerts very strong electrical forces on its neighbors. That polar property of water as a molecule makes it have a lot of cool physical properties. It has a high specific heat. It has a large, it stays liquid over a really large range. It's hard to evaporate water or to boil water compared to a lot of other liquids. But the other thing it does is it makes it really good at dissolving stuff. If you put salt in water, it dissolves. If you put sugar in water, it dissolves. If you wash your clothes in water, the dirt and stuff on your clothes dissolves and goes into solution. Your body is just a big chemical solution. What does your body need water for? Your body needs water to dissolve the nutrients and the chemicals that your cells use to make a chemical metabolism, to have chemical reactions that are being alive. Methane is not as good at dissolving stuff as water. It's very, very simple. Can we imagine a chemistry that exists in methane where the organic chemicals are dissolved in methane instead of water? Harder to imagine than just imagining that happening in water. So we don't know. There are astrobiologists who have imagined a chemistry that instead of being based on amino acids, which is what our chemistry is based on, all of our proteins are made of amino acids, which look like this. It's an NH2 and then a CH and then a COOH. Could be made of, and this is organisms on Earth put together amino acids out of carbon dioxide, oxygen, and water, which are common on the Earth. We can imagine a different kind of chemistry where the compounds that are available are methane and nitrogen instead of CO2 and oxygen. And without water, we can imagine putting together, notice the H2O here in the amino acid is replaced by these nitrogen groups, these amine groups. Instead of amino acid, this is called a, what is this called? I'm not a chemist. It's called an aminoamidine instead of an amino acid. So it's similar to an amino acid in that it's got this carbon that you can connect other chunks to, and this is what makes different amino acids different. Again, I'm not a chemist. You guys don't have to remember the exact chemistry of this. Suffice it to say that amino acids are a class of chemicals with different stuff attached to this carbon that make different amino acids. We can imagine aminoamidines with different stuff attached to this carbon that don't need any water because they use methane instead, and would be a completely different biochemistry based on a completely different set of building blocks for those organic molecules. Is this really possible? Nobody knows. The only way to know is probably to go back to Titan, to swim around in the oceans of Titan with robot submarines to gather these chemical compounds and to see if we can find traces of something that looks like an actual biochemistry as opposed to just simple organic chemistry. And we can imagine a whole complex cycle. I won't get into that. Again, this is still hypothetical. There is the possibility that inside of Titan, after you get through the icy, rocky crust, there is a layer of liquid water under the pressurized ice and then a rocky core below that. Are we sure about this? No, we're not sure about it, but just like the evidence for Europa and Ganymede is getting stronger and stronger over time, the evidence for a subsurface ocean on Titan is getting stronger and stronger over time. So beneath the rock and ice, between the icy layer and the rock ice layer, there could be a layer of liquid water, maybe a mixture of water and ammonia. So just like Europa has got an ocean that covers the whole moon, maybe the same thing is going on in Titan. We don't know yet. So what are our plans for going back to Titan? Just like I said about Europa, I don't believe there are any missions to the Saturn system that are beyond the drawing board phase. But Titan offers some real different possibilities for exploration than, say, Mars, because of the thick atmosphere, where you could build a blimp that floats around on Titan and explores it by just floating through the air instead of having to drive over the rocky, bumpy surface. You could build a quadcopter, a flying drone that flies around in the thick atmosphere of Titan, it would be actually easier than building a quadcopter that works on the Earth, right? Because Titan is smaller, so the gravity is less, but the atmosphere is thicker. So you could actually fly a quadcopter around, a drone around on Titan easier than you can fly one on the Earth. Also, if there are bodies of liquid, you can imagine sending a submarine to Titan, a robotic submarine to swim around in the liquid methane and ethane lakes and analyze the chemistry directly. There was a plan for a TSSM Titan Saturn system mission, which was supposed to have been launched 2 years ago and was not. So again, NASA often suffers from missions that are planned but scrapped, and hopefully we will have a mission, a concrete mission to Titan planned soon. But that mission had plans for a boat to sail around on the seas of Titan, and basically a hot air balloon to float around in the atmosphere of Titan, allowing it to move much further than a rover that drives around on wheels and needs battery power. One of the other things that makes it easier to explore Titan than a lot of objects in the solar system is that you can land with a parachute. Landing with a parachute is way easier than landing with rocket engines that slow your descent, because those rocket engines need fuel, and that fuel is heavy, and it makes your whole spaceship more expensive to get off the Earth in the first place. You can't really use a parachute very well on Mars. It'll slow you down a little, but Mars's atmosphere is so thin that it can't be your only way of controlling your descent. But with the thick atmosphere on Titan, you can actually use a parachute to slow your descent, and it's actually way easier to land on Titan than it is to land on a lot of the other objects in the solar system. We're about a half an hour now. I want to really, really quickly talk a little bit about one of Saturn's other moons called Enceladus, because it is another example of how when we flew these missions past Jupiter and Saturn in the 80s and then again in the 90s with Galileo and Cassini, early 2000s, Cassini-Huygens probe, we discovered some things that were unexpected. This is Enceladus. It's one of the smaller spherical moons of Saturn. At first glance, it's like, yeah, that's a boring moon like our moon, right? It's covered in craters. It's kind of gray and boring and rocky until you look at the southern region here and you see these long parallel streaks. And you're like, well, those are interesting. There's nothing like that on our moon. So what's going on there? We noticed something weird about Enceladus. I think Voyager actually discovered this back in the 80s. I could be wrong. Maybe this wasn't until Cassini. But looking back towards the sun, where Enceladus is backlit, we saw this material coming off the surface of Enceladus, something being emitted from the surface. Like a volcano or a geyser, a material boiling or sublimating off the surface the way it does of, say, an icy comet, as an icy comet gets close to the sun. But it's not hot out where Enceladus is. So what could be the source of energy that is causing this material to evaporate or boil off the surface? It would have to be something from the inside. Here's a color photograph showing that same view of this material being emitted from the surface of Enceladus into space. Here's a highly processed, highly contrastified false color image of that same thing, showing that this material actually is emitted quite a distance out into space, and sort of there's a ring of gas and ice crystals orbiting Saturn in Enceladus's orbit. What's going on here? One clue to what's going on is when we measure the temperature of Enceladus with an infrared camera. This is what you would expect the heat map of a moon that's lit by the sun to look like. The equator is warmer, so this is an infrared false color. Well, this is a simulation of an infrared map of Enceladus, and the red represents warm and the blue represents cold. Not very warm. The red represents 80 degrees above absolute zero, 80 degrees Kelvin, and the blue represents 60 degrees above absolute zero. So instead of warm and cool, you can think of this as really, really cold and just a little cold. But you would expect it to be warmer at the equator because the equator of a planet gets more sunlight. That goes for every planet, including the Earth. That's why it's warmer at the equator. When we measure the temperature of Enceladus with an infrared sensor on our little orbiting spacecraft that we send out to Saturn, this is what we found. At the South Pole, it is way warmer than it is at the equator. That doesn't make any sense if the source of the heat is from the sun. This means that the source of this heat is from the inside of Enceladus. And we don't really understand what the source of that heat is, which makes Enceladus an interesting object. I thought there was a picture of the stripes. I have a picture showing those stripes, showing that those stripes in the South Pole of Enceladus are actually warmer than the surrounding surface, suggesting there is heat from the inside of Enceladus kind of welling up to the surface. What are some of the models for what's going on inside this moon? The idea is that the moon is being heated from the inside, either by radioactive decay or by tidal heating, or a combination of the two. And that causes, the surface is mostly ice, but that causes a region below that to be partially melted. Think of it as like the consistency of a Slurpee. So it's not completely liquid, but it's a slurry of frozen water and maybe liquid ammonia. And this material can warm the solid ice above it to the point where it sublimates or evaporates into space. And so what we're seeing in those pictures is the surface ice being turned into vapor by this heat from inside of Enceladus. This is called the sublimation model. It's just being warmed up enough to turn from, sublimation is when you turn directly from a solid to a gas, like what dry ice does here on the Earth, right? If you have a block of dry ice, frozen carbon dioxide, it doesn't melt into liquid. It just evaporates straight into a gas. That process is called sublimation. So that's what would be happening here on the surface of Enceladus. The surface ice being warmed from underneath just sublimates into gas that is then drifts off the surface, and that's what we're seeing in those images. A more interesting model is the cold geyser model, or the cryovolcano model, where the heat from the interior actually causes pockets of liquid water under the surface to become pressurized until they burst out of the surface like Old Faithful, like a geyser on the Earth, and that burst of water through the surface we call a cold geyser. This is the preferred model currently, and the reason is when we do analysis of these plumes of material coming off the surface, we find not just water vapor, but we find particles of ice, like snowflake and like imagine getting a snow cone, right? Those little chunks of ice in a snow cone. We find chunks of ice in these plumes that are coming off the surface of Enceladus, which wouldn't happen if it was just sublimating gently off the surface. It would only happen if it was exploding out of the surface and sending chunks of ice up into space along with the water vapor. So the cold geyser model is right now the favorite explanation for what's going on the surface of Enceladus. Why is this interesting? It's interesting because, again, here's a place where maybe there's liquid water underneath the surface of an object in our solar system, and that liquid water is being heated by some source of energy. And anytime we find liquid water and a source of energy, our brains immediately go to, could something be alive in there? On Enceladus, I don't know. It seems far-fetched to me, but it's not impossible. We've also found trace elements of organic compounds, simple chains of carbon atoms connected to hydrogens and nitrogens and other things. Things like methane and benzene and acetylene and formaldehyde, and even some larger, more complex organic molecules. Is this proof that there's life in the pockets of water underneath the surface of Enceladus? No, not at all. But it is encouraging evidence that the processes that we think are precursors to life and biochemistry are so common that we even find them on dinky little weird moons out in the outskirts of our solar system. And if these processes are so common that we even find them on dinky little weird moons in the outskirts of our solar system, maybe they are actually very common throughout the universe. So the more organic chemistry we find, even the simplest organic chemistry, the more confident we become that maybe life, even if it's not on Enceladus or Titan or Ganymede or Europa, might be more common than we would think. Because the more examples we have of carbon atoms doing interesting things, the more possibilities there might be for the culmination of that process, which is actual organic chemistry. So if we look at our solar system, we've got the Earth, where we know has life. We've got Mars, which we know, we're almost certain, had liquid water on the surface in the past. We've got Europa, Jupiter's moon, and Ganymede, Jupiter's moon, which we think have subsurface oceans. We've got Titan, which has incredibly interesting organic chemistry in the atmosphere. We've got Enceladus, which we have pockets of heated water under the surface. And suddenly we're up to 4, 5, 6 places in the solar system that are candidates, even if we're not optimistic about it, are candidates for possibly having the conditions for life, which is 3, 4, 5 more places in the solar system than people would have guessed, say 40 years ago. They might have said, definitely Earth, maybe Mars, nothing else. Well, now we're not so sure. We're thinking bigger and differently about what the possibilities are for life in our solar system and beyond. And we'll talk about that. We'll talk about our ideas concerning what it would take for life to get started on the planet in a separate lecture.